Hello everyone and welcome back to this series. In this series, we'll be looking at questions from chapter 7 or chapters 5 and 6 that involves exercise 7. So in this series, we'll be looking at how to derive material index. So if you look at what I have on the screen, it involves the steps to derive material index. So if you understand these steps, this course will be very easy for you. So this is like the basic foundation in deriving material index and passing through this course. So depending on the situation, it can be multiple constraints, multiple objectives. You have to understand these steps in order to pass this course. So the first step is look at the table obtained from the translation step. So in the translation step, you have to derive the function, the constraint, objectives, and free variable, right? And free variable. So that's what you do in the translation steps. So that's what you're doing in the translation steps. So once you have done this, you can now look at the question critically based on this. So the next step is derive objective function. So you have to write down the objective function. So this is the objective, and objective is usually minimize this or maximize that. So let's say we are trying to minimize mass. So you have to just write down the function for mass, which is mass is equals to volume times density. You understand? And you have to try to break it down in order so that the formula for the objective function will contain the free variable. Let's say the free variable is thickness. You have to break it down as mass is equals to area times thickness times density. So that's how you have to write it down. So next, you have to write down the constraint function. Let's say the constraint is stress or strain. Or stress, let's say it's stress. You have to write down the constraint function. So you write down the constraint function as stress. Let's say stress is equals to Young's modulus times strain. So that's the constraint function. So once you've written down the constraint function, like you did with the objective function over here, you have to break it down so that the constraint function will contain the same free variable that you have here, which is thickness. You have to make sure that the constraint function contains the same free variable. So you have to break this down in order to add the constraint function. And you know that strain, the formula for strain is equals to change in length over original length over LO, original length. So you have to find a way. Let's say the length that you're talking about is the length that you're talking about is the thickness of the material. Let's just assume is the thickness and say E is equals to change in length over thickness. Let's say LO is the thickness. So right now your stress will now be equals to E times change in L divided by thickness. Let's just say that's the case. So what you now have to do is eliminate free variable from the two equations. In order to eliminate free variable here, you have to make thickness here subject to the formula. You now say thickness is now equals to E change in L divided by stress. So that's what you're going to say for this. So now you have your thickness equation. You now have to eliminate free variable from the mass equation, and then mass will now be equals to A. Then you now add this equation, E change in L divided by stress times density times density. So that's now your formula for mass. That means you have eliminated thickness from the objective function. You've eliminated thickness. So that's it. So once you've eliminated thickness, the next step, let's go back to our next step. The next step says once you've eliminated thickness, once you've eliminated the free variable, then you now obtain the expression for the free variable from the constraint equation, then plug it into the objective function. So that's what we did. We just did that. Then you can now divide the objective function to functional constraints, geometric constraints, and material properties. So that's what we are trying to do. We are trying to divide this equation to functional constraints, geometric constraints, and material properties. So if you look at this equation, what do you think is going to be a functional constraint? So the functional constraints are like constants in the material, functional constants in the material. So if you look at this, so let's say mass. Okay, let's just break it down for material properties first. Let's say property of steel. Like, what are the properties of steel that you can get from this equation? So area is not a property of steel. Area is not a property. You can't say that this steel always has an area of this, but you can say steel has always a Young's modulus of this, and you can say that steel has a Young's and a stress of this can withhold a stress of this, a fracture stress or fracture stress or yield strength, or you can say this. Then you can say the density of steel is always this. So everything that has to do with a material property, you write it as E, which is a material property, times density, which is a material property, over stress, which is a material property. So these are your material property. So times. Next, let us write down the geometric constraint. Geometric constraint is like the geometry of the material, something that limits the geometry of the material. Let's say it's the area. let's say the area is the geometric constraint, you can now write it as what? Area, as the geometry. Maybe the area has to be constant, the area doesn't have to change, right? Then the functional constraint is like all the constants in the equation. So every other constant in the equation can be what? Changing length, which is every other constant. So right now we have what? Here geometric constraint, here functional constraints, and here is what? Your material property or your material index. So you can now bring out your material index. Your material index as m is equals to Young's modulus times density over what? Stress. But this is what? Always what? This is what? Minimization. This is what? Minimization. But most times, most textbooks write this in terms of what? Maximization. So that's why you can get the inverse of this equation and write your material index. M is equals to what? Stress over E times what? Density, which is what? Your material index, which is what? Maximization. So whenever you solve this equation, always let the professor know that this is minimization or this is what? Maximization, depending on the situation. So let us go to what? Exercise 7.1 right now. So guys, for question 7.1, take a second, pause the video and read the question. So for this question, I don't want to go through all the write-ups that they've done here, but luckily enough, they have already derived what? The function, constraint, objectives, and what? Free variable for us. So the first step in deriving a material index is to get what? This table over here. That's the first step. But since they have already given us the table, I'm just going to tell you what the question is talking about. So for the question, we are trying to derive this material over here called the aperture grill. This this material over here, the aperture grill, that's what we're trying to derive, and it has what? A series of wires that have been what? Pre-stressed, like the material have been extended. All this material have been stressed a little bit, like some kind of tension have been put on this material. So once you put a tension on any material, it has to undergo some kind of what? Stress, E, some kind of strain, E, some extension or strain. So this material have already been pre-stressed and some kind of extension have been induced in this material. And this material, electron beam is passing through this material. And if this electron beam passes through this material was heats up to a particular point. And you don't want some expansion, like another expansion based on the heat, because if you're heating up the material, a material what? Expands, and you don't want an extra what? Expansion. You don't want an extra extension in this material because you've already what? Extended this material to a pre-stressed or pre-extended what? Length. So you don't want an extra extension. So based on that, we have what? This, the function, constraint, objective, and free variable. And the function is what? An aperture grade for what? A cathode ray tube. So that's the what? A function. The constraints are the wire thickness. The thickness of the wire is specified and you can't go over it. The material must carry a pre-extension or pre-tension without failure. It must carry some kind of tension without failure. So the next one is what? Electrically conductive. So the material must what? Be electrically conductive to prevent what? Charging. Then the next step is what? The next constraint is what? Able to be drawn into wire. So it must be what? Ductile enough to be drawn into what? Wire. Then the next one is what? Objective function. So the objective function is what? Maximize what? Permitted temperature rise without what? Rising what? Tension. So we want a material that can increase in temperature without what? Expanding. So less expansion in the material. So the free variable is what? The choice of material. So since we don't have what? A free variable that is a function or a function that we can substitute or remove, we just need to what? Derive what? The objective function. That's all we need to do for this question. So the objective here is what? To maximize what? The objective function. So the step one. So you look at the steps that I gave in the start of this video. There are steps you have to follow. So the first step is what? Derive the objective function. So step one, derive objective function. So that's our first step. So that's what we're trying to do. And our objective is what? To maximize permitted what? Temperature. So we are trying to maximize what? Temperature. That's what we're trying to maximize, and minimize extension or loss of tension. We're trying to minimize what? Loss of what? Tension or loss of tension, and minimize E. That's our goal, where we're trying to maximize E. So as the temperature is going up, we don't want the material to what? Expand so much. So that's what we're trying to do. So there are two types of extension that is going on in this material. So the first one is what? Pre-extension because of what? Tension. So the first extension that is already in this material is the pre-extension due to what? The pre-strain in the material. So first extension that is going through the material is E, which is what? Due to what? Pre-extension. Is giving us what? Stress over what? Young's modulus, because we know that Young's modulus is equals to what? Stress over strain. So this is due to what? The pre-extension in the material. So that's the first extension that is going through the material. So another extension that is going through this material is the extension due to what? Increase in temperature. So the extension due to increase in temperature is giving us what? Extension due to what? Change in temperature due to heat. Because as the cathode ray tube is heated up, the material heats up and you don't want the material to what? Extend. So due to heat is giving us what? This is thermal expansion, coefficient of thermal expansion times what? Change in what? Temperature. So that's the second pre-extension. So this material have already been pre-extended, and as you're heating up the material, there is also additional extension in this material. So we are trying to what? Maximize what? Temperature while minimizing what? This extension. So you don't want this extension to be above what? The extension due to what? Pre-extension. So we want extension E due to what? Pre-extension to be greater than what? Extension due to what? Heat. So that's what we want in this particular question. So greater or equal to this. So you can now what? Input their formulas into each of the equations. So you know that this is equals to what? Stress over Young's modulus, which is equals to, let's just use an equation sign, like equals to thermal expansion times what? Change in temperature. And our goal is what? To what? Maximize what? This man over here. We're trying to what? Maximize this material over here. So make this subject formula. That means change in T is now equals to stress over E divided by thermal expansion. So now we have our objective function. So this is our what? Objective function. So this is our objective function. So you know that this is the first step, is to derive the objective function. The second step is to what? Derive the constraint function. But here we don't have what? A free variable. Whenever you don't have a free variable, whenever you don't have a free variable, the objective function, you just stop at what? Step 1, which is what? Derive objective function. Then what? Move to the last step, which is what? Getting what? Geometric constraints, functional constraints, and what? Material properties. So we need to break down this into what? Geometric constraints, functional constraints, and what? Material properties. So if you're looking at this, we don't have any geometric constraints and we don't have what? Any functional constraints. All we have here is material property, because what? Stress is a material property, Young's modulus is a material property, and coefficient of thermal expansion is a material property. Therefore, our material index M is now equals to stress divided by Young's modulus times what? Times thermal expansion. But this, you always write that this is what we are trying to maximize, right? So this is what? Maximization, right? Trying to what? Maximize this. So just always make sure that you write that this is maximization. Always. That's what we're trying to do, because we're trying to what? Maximize what? Temperature. So if you're trying to maximize temperature, so you're trying to write maximize what? This function. So you always write that is either maximize or minimize. But most textbooks write their material index in terms of maximization. So you always want to leave it what? In maximization. So let us go to what? 7.2. So guys, for question 7.2, take a second, pause the video and read the question. So in this question, we are looking at deflection for cantilevers. So there are different scenarios or different loading conditions for different types of for different cantilevers. So different loading conditions. So here you have A, B, C, and D. So for A, you have what? Fixed area for the cantilever and fixed length. For B, you have what? Fixed length and fixed what? Area. Then for C, you have what? A free area but fixed length, right? Then for D, you have a free area and fixed length. Then A and D are what? End load cantilever. So you have loading conditions at this point. Then for B and C, you have what? A loading condition that is throughout the beam, not an end load condition. So if you read the question, you can see that this formula, the formula for deflection D, the formula for deflection delta, this is for what? End load deflection, and this is for distributed load deflection over here. So what is deflection? Deflection is what? The bending of this beam from this to a point somewhere here. So that's deflection. So if you look at the formula closely, you have what? They have given us all the formula for deflection for both conditions, and they're giving us the formula for I for a square shape area. So the cross-sectional area is a square. So the formula for a square shaped cross-sectional area, the formula for I, which is what? Moment of inertia, I. Moment of inertia that helps the beam to prevent what? Deflection, I, is giving us what? T4 divided by 12. So that's I here and I here. They have given us the formula for both I. they've given us formula for I, and for distributed load, they've given us formula for F as was this, which is what density times area times G, which is what acceleration due to gravity. So we have different questions A to D that we are trying to solve. So for A, let us go with A first. So for A, they say that let us show that the material for the cantilever beam L is given. So given L, so L is fixed, the length is fixed, and a given cross-sectional area. So given area. So that means for this condition given in figure A, where length is fixed and what cross-sectional area is what fixed. And they said let us find the least deflection. So we are trying to minimize what deflection. Show that the material with what the least deflection under a given load F with the highest value of material index M is equals to E. So they told us to find the material index, to derive the material index M equals to E. So that's what they're trying to tell us, where E is what the Young's modulus. So this is what we are trying to do. So first, let us list out the function, constraint, objective, and what free variable. So first, you know that the function F is equals to, so this is an end load cantilever. So end load, so we have an end load cantilever. So that's the function. Then the constraint, we have a constraint. So we have what constraints are what length, comma, cross-sectional area, that's comma, and what specific what load F, that's the function, that's the constraint. And you can look at what the objective here is to what minimize. We are trying to minimize what deflection that we are trying to minimize. Then the free variable F is equals to what choice of material. So you always know that what I told you before, that anytime you're looking for the material index, and the choice and the free variable is just choice of material and not a function like thickness or length or any other free variable. Once the free variable is just choice of material, so how you derive the material index is just to derive what the objective function. So the objective function here is what minimize what deflection. So we are trying to what minimize deflection, and the formula for deflection for an end load material is giving us what deflection delta is equals to FL raised to power 3 divided by 3EI. And the formula for I is giving us what I is equals to T raised to power 4 divided by 12. That's the formula for I. Therefore, deflection is now equals to 4 times what FL3 divided by T raised to power 4E. So that's the formula for deflection. So now you have what this is what your objective function. And since you don't have what a free variable to eliminate, that means you now jump to the last step, which is what you have to divide the objective function into what functional constraint, geometric constraint, and material property. So first, let us write out the material property. So the material property is what E. That's the only thing that is a material property. So force is not a material property, length is not a material property, and thickness is not a material property. So our objective function, our material property is 1 over E times, then the functional constraint, the geometric constraint, which is what constraint based on what geometry, and the constraint based on geometry is what L3, which is what the length, because the length was fixed, and what the thickness as well, which is what the area was fixed as well. So thickness raised to power 4 is a geometric constraint. Then all other constraints is what functional constraint, which is what 4 raised times what F. So if you're looking at this is what geometric constraint, and this is what functional constraint, and this is what material property. Therefore your material index M is now equals to 1 over E, because your material index is always what material property, and this is what you're trying to what minimize. You're trying to minimize, because we are trying to what minimize the objective function deflection. That means you're trying to minimize this. But I told you before that material index is always written in terms of what maximization in most textbooks. So in order to write this in terms of maximization, your material index M will now be equals to find the inverse of 1 over E, which is what E. So your material index is what was this, which was maximization. So that's your answer. Let us go to question B. So for question B, they are trying to tell us to find the material index for this condition, for this loading condition, where you have self-loaded or distributed load. And so we are looking for what this formula, right? So for the distributed load, so first we have to find what the function, constraint, and objective and free variable. So for the function F is equals to, the function here is what a distributed load cantilever. So cantilever. So that's where we are looking for a distributed load cantilever. So for that's the function. The constraint. So the constraints are still almost the same like the other ones. So we have what? A specified length, a specified what? Area. So that's the distributed load, a specified area. Then the objective here is what? We're trying to what? Minimize deflection. That's the objective. And the free variable is equals to what? Choice of material. So since that our free variable is just choice of material, that means all we have to do is what? Define what? The objective function and get our what? Material index. So for this situation, first we know that for this situation we know that the deflection that we are using, the objective function for the deflection is equals to 1/8 f L raised to the power 4 divided by EI. That's our formula for deflection. So all we now have to do, we have to what? Put the equation. We now have to insert I. We have to insert both I and what? F. We know that I is equals to T raised to the power 4 divided by 12, and F is equals to, let's see what F is giving us, what? Density. So density times what? Area times what? Acceleration due to gravity. So we need to put this into this what? We need to put these two into this what? Equation for deflection. So once we do that, we now have what? Deflection as what? 3g L raised to the power 4 times what? Density divided by 2t squared. That's what we have times what? Young's modulus. That's what we have as what? Formula for deflection. So next, since we don't have what? Free variable, you don't have to what? Define what? Constraint function. You just go straight to what? Breaking down this equation into what? Functional constraint, geometric constraint, and material property. So if you want to break it down, you now write what? Deflection is equals to, so which of these is a material property if you're looking at it critically? So acceleration due to gravity is not a material property, length is not a material property, density is a material property, then thickness is not a material property, but Young's modulus E is a material property. So you now bring down the material property as what? Density divided by Young's modulus E times, next one is what? The geometric constraint, the geometry of the material. So based on the geometry of the material, the constraint that we have what is what? L4 raised to power what? Thickness raised to power 2. So that's the geometric constraint, and the functional constraint is now everything left in the equation, which is what? 3g divided by 2. That's the geometric constraint. So right now your material property M, your material index M, is now equals to density divided by Young's modulus. But this is what? Minimization, because you're trying to minimize what? Deflection. But in terms, you always have to leave this in terms of what? Maximization, which is what? M is equals to Young's modulus divided by density. So this is what? Maximization. So let's go to question. So guys, for question C, 7.2c, here we are trying to find the material index for this particular loading condition C. So they say that show that the material index for a light cantilever beam, so the light cantilever beam, so that's the objective, a light cantilever beam of length L. So this is fixed, constraint fixed, and has a square section that is not given. So this is free. Okay, they also said like the area is the free variable. So the area is what? The thickness times thickness, which is what? Thickness raised to power 2. That's the area, and which is a free variable. And they said that will not deflect. So deflection more than a delta under its own weight. So the deflection is a constraint as well. And they've given us the material property as M is equals to E. They've given us the material index as what? M is equals to E divided by density raised to power 2. So they are telling us to derive this particular equation. So based on this, first let us define what? Function, constraint, objective, and what? Free variable. So first we have the function. The function of this is what? A distributed load cantilever beam. A distributed load cantilever what? Beam. That's a function. The constraint here, we have different constraints. We have what? Length L and what? Deflection. That's the constraint. Then the free variable that we have here, sorry, let's define what? Objective first. You have to define objective first. So the objective is what? We are trying to what? Minimize what? Mass. And the free variable FV is equals to what? Area, which is what? Thickness raised to power 2. And what? We have the area, and we have what? Choice of what? Material. Choice of material. So like the other questions that we've been solving, we don't have what a free variable. We always have what just choice of material as free variable, but right now we have area as choice of material. So here we have to follow all the steps for deriving what material index. So step 1 will now stay step 1, which is what derive objective function. That's the first step. That's the first step that we are trying to follow. So first, we now know that our objective function is mass. So mass m is equals to what? Volume times what? Density. But you always want to derive what? Volume mass, your objective function, in terms of what? The free variable that you're trying to eliminate, because you will eliminate free variable at the end of the day. So you're trying to define this objective function in terms of what? The free variable. So mass, you can now define mass as what? Area times length, because that's the area, cross-sectional area times the length, right? Times what? The density. So you can now break down this cross-sectional area as well as m is now equals to what? Thickness raised to power 2 times length times density. So right now you have derived what? Objective what? Function as equation 1. So that's our first equation. So step 2. So derive what? Constraint function. So that's step 2. So our constraint here, if you look at our constraint, is what? Deflection. So deflection is our constraint here, and they told you that the formula for deflection for a self-loaded or distributed load is given as what? This particular equation over here. So we're going to write it out, and also we have other formulas inside it. We have F given as this, and we have what? Moment of inertia given as this. We have to input these two into this what? Equation for what? Deflection. So that's what we're going to do. We're going to just write it out for the equation for what? Deflection. So that's exactly what we're going to do. So in the last case where we did this particular equation in question B, that's what we're just going to write it out as what? Deflection is given as what? 3 right F L4 raised to power divided by 2 E t raised to power 4 et raised to power 4. That's if you include what? ei over L. That's if you include what? ei over 12. So that's when you include ei over 12. So if you now include F into this equation, if you now include the formula for F, you now have what? 3g L squared L raised to power 4, sorry, so 3g L raised to power 4 divided by 2t squared divided by E times what? Density. So that's the formula for our deflection. So that's what we are solving with, the formula for deflection that we are solving with in this particular question. So now that you have this, you're trying to what? Eliminate what? Free variable. So the free variable in this question is what? T raised to power 2, because T raised to power 2 is here and T raised to power 2 is here. So you're trying to eliminate T raised to power 2 from the what? Objective function. So step 3. So first, let us make T raised to power 2 subject to the formula. So T raised to power 2 will now be T raised to power 2 will be equals to 3g L raised to power 4 times density by divided by 2 deflection times what? E. So that's the formula for deflection. So, since you have this as what? You've made t squared subject to the formula. Now you have to what? Eliminate t squared from the objective function. So step 3, eliminate free variable. So that's what we're trying to do. So we are going to input this particular equation into this one. So we have what? Our formula for mass will now be equals to 3gl. So that's what we're trying to do. So thickness, we are trying to write tgl raised to power 4 times density divided by 2 times what? Deflection times E. Then we now have what? Length times what? Density again. So right now, since we now have this, we can now break down. We need to break down into this into what? So step 4. So break down the equation. So in order to break down this, we have to write what? Geometric constraints, functional constraints, and what? Material property. So like we did before, the material property is first. That's what I like always writing first. So for the material property, density is a material property. So density, you have density squared as a material property. So you write out what? Density squared as a material property. Length is not a material property. Acceleration due to gravity is not a material property. Deflection is not a material property. But Young's modulus E is a material property. So you write down divided by E. So that's the material property you're looking for, divided by E. So times, so what are the geometric constraint? The geometric constraint from the question that we have are just what the geometric constraint are the length, the specified length of the material. That's the geometric constraint that we have, which is L raised to power what 5, because we have L here and L here raised to power 5, and every other thing is what a functional constraint, which is what 3G, 3 times G, that's what we have, or all that we have here, divided by 2 times what deflection. So this is what functional constraint, this is what geometric constraint, and this is what material property. So your material index M will now be equals to density squared divided by E, and this is what minimization. But you're trying to write this always in terms of what maximization. That's why you write what M is equals to what E divided by density raised to power 2, and this is what maximization. So that's so guys, for question D, so here if you take a second, look at the question. They're telling us to find the lightest cantilever. So here you see the lightest cantilever beam. So that's what we are trying to find. This is the objective light material. So we're trying to reduce what the mass with a length, a specified length L, and a square cross-sectional area. So the area is free. So this is a free variable area that will not deflect more than the deflection D under a specified end load. So this is the particular scenario that we are looking for. So this is the scenario. So an end load of D. So D is what a constraint of the material, and they told us that the material index is this, and they told us to what derive this material index and neglect self weight. So first we have to derive function. So the function here is end load cantilever beam. So that's our function, right? Function, our constraint, let's derive constraint. Our constraint is equals to what? First we have a length, specified length that is specified. We have a specified end load F and a specified what deflection, which is deflection, right? That is right this. Then we have our objective is what we are trying to what minimize. We are trying to minimize what mass. That's the objective. And the free variable is what area, which is what T raised to power 2, and choice of what material. Choice of what material. That's our free variable. So same thing like the other one. Since we have an area as part of the free variable and not just choice of material, we have to follow all the steps for deriving material index. So step 1, define or derive objective function. So the first thing that we're trying to do, our objective function is what? Mass. So mass is equals to volume times density. That's the formula for mass, which you can say is equals to as well. Mass is equals to, which is what? Area times length times what? Density. So also we can define area in terms of what? Thickness, which is what? Thickness raised to power 2 times length times density. So these are equation for objective function. So step 2 is derive constraint function. So that's step 2. So step 2, our constraint here is what? Deflection, and deflection encompasses the force and what? The length. So the formula for deflection, which is given by this equation, and we are looking by this particular equation because we are looking for what? Straightforward, like an end load deflection. That's what we are looking for. We're not looking for a single load deflection, so we are looking for an end load deflection. So deflection is what? Deflection is equals to FL raised to power 3 divided by 3EI, and I is given as what? I is given as what? T4 divided by 12. That's our I. So we put our formula for I into the formula for deflection, right? We need to put our formula for I into the formula for a deflection to get our deflection equation. We have what? Deflection as 4 times F raised to power L times L raised to power 3 divided by T raised to power 4 over E. That's our formula for deflection because we have added what? I. So right now the next step is what? Let us make the T. We are trying to make what? T squared subject to the formula. So not T. So here we have what? T raised to power 4. So we are trying to make T squared subject to the formula. So in order to make T squared, because we are trying to eliminate what? T squared from this equation, which is the area. So making T squared subject to the formula, we have what? T squared is equals to 4 raised to power FL3 divided by E. That's what we have. So all raised to power what? 1 divided by 2. That's what we have. So in order to open up this equation, right, if you're trying to open up this equation, you have to have t squared is equals to 2f half L3 divided by 2 divided by E half. That's how you open up the equation. That's why. So you now have the next step is what? Step 3. We have step 3. Sorry. We have what? Eliminate free variable. So in order to eliminate this free variable t, we have to eliminate t from the objective function, this t over here. So all we have to do is what? Write out our mass. Mass is equals to, we write out this 2f raised to the power half L raised to the power 3 divided by 2, all divided by E raised to the power half times length times what? Density. So the next step is now what? We have to break down the equation. Step 4, break down equation. So that's the next step. So you're trying to break down this equation into functional constraints, geometric constraint, and what? Material property. So which of these is a material property? So first, let us write M is equals to density is a material property and Young's modulus is a material property. Every other thing is not a material property. So what you have here is what? Density divided by Young's modulus raised to the power half times, next one is the geometric constraint, and based on the constraint that we defined, we know that the geometric constraint is what? Length. The length is the geometric constraint. The constraint based on what? The geometry, right? So that's what we're trying to write down. So the constraint based on the geometry is what? L raised to the power what? 3 divided by 2. So that's a geometric constraint. And every other thing in this equation is now what? Functional constraint. So we now have what? 2f raised to the power half as our part of our functional constraint. That's 2f raised to the power half. Then every other thing has gone as what? Functional constraint. Also, if you look at this L here times L raised to the power 3, L3 divided by 2, that's what we have. So if you put here, this will now turn into what? 5. So that's what it has to turn into. This has to turn into what? 5 divided by 2 instead of what? 3 divided by 2. So now you have this. You can now write this as what? This is what? Functional constraint. This is what? Geometric constraint. And this is what? Material property, right? So our material index M is now equals to what? Density divided by E raised to the power half. This is what? Minimization. But you're always writing this in terms of what? Maximization. So M will now be equals to what? E raised to the power 1 divided by 2 all over what? Density. So this is what? Maximization. So this is our answer. So now we are going to move on to. So guys, for question 7.3, you can take a second, pause the video and read the question. In this question, they're telling us to find what? The material index for a beam. So if you can read the question, that's good, but they have already derived the function, constraint, objective, and what? Free variable for us. So the constraint here is the specified length of the beam L, which is here, and they also one of the constraints is the beam must support a bending load F without what? Yield or fracture. So the bending load F is giving us what? This equation over here. The bending load F of a beam is giving us this equation over here, which they have already given to us. And the objective function is what? Minimize what? Mass M. So minimize mass M, and the free variable is what? Choice of material, and the cross-sectional area A. So since the free variable is what? Giving us what? Area, that means we have to follow all the steps in deriving what? Material index. So step 1, which is what? Derive objective function. That's step 1. So for step 1, our objective function is what? Minimizing mass. So mass is equals to what? Volume times density. And also, I told you that you always derive a mass in terms of what? The free variable, in this case, which is A. So mass is giving us is equals to area times what? Length times what? Density. That's the formula, which is our equation 1. So equation 2, step 2 is what? Derive constraint function. That's step 2, and our constraint is giving us this equation over here. That's our constraint, which is what? F is equals to I times what? Stress times what? The stress all over Ym times what? Length. And note that Ym in this question, Ym is giving us what? Is the distance between the neutral axis and of the beam and its outer filaments. That's the formula for Ym. So Ym is now giving us Ym m is equals to, so if you look at a beam, if this is the cross-sectional area of a beam, where this is the thickness times what? Thickness, because we have what? A square cross-sectional area. That means the neutral axis is somewhere in the middle. The neutral axis is somewhere in the middle, which does not bend. Somewhere in the middle. Here, let's say here, which does not bend. Therefore, ym is giving us what? The distance between the neutral axis and the outer edge, which is ym, which is giving us what? Thickness, which is the thickness of the material, thickness divided by 2. So that's ym is equals to what? Ym. So we now put ym into this equation. Putting ym into this equation, we now have what? F will now be equals to, if you put ym into this equation, it will now be F is equals to 2i rho for F divided by TL. So that's our formula. That's our formula for F, because we've now added what? Ym into the what? Equation. So next we'll now derive what? The formula for I, because I is already given here as what? I is giving us this particular formula, T4 divided by 12. So I is now giving us what? I is equals to T raised to power 4 divided by 12. In order to put this equation, this into what? This equation, we have to substitute I for I. So 2 will now cancel this, into will now be 6. T will now cancel this, is equals to what? T raised to power 3. That means our F will now be equals to T raised to power 3 rho F divided by 6 what? L. So that's our rho F, right? So that's our rho F. So next, we now know that our free variable is A. If you look at our free variable is what? Area. That's what we are trying to define, our free variable. So our free variable is not what? Thickness. So we try and define what? Thickness in terms of what? Area. So defining thickness in terms of area, that's what we are going to do. We know that area is equals to what? Thickness raised to power 2. And what? Thickness is equals to A raised to power what? Half. That's what we know. Therefore, thickness raised to power 3 is equals to area times what? Area raised to power 1 divided by 2, which is equals to what? Area raised to power what? 3 divided by 2. So we now put this into this equation. That means F will now be equals to area raised to power 3 divided by 2, area divided by 3 divided by 2 by stress raised to power F, stress F divided by 6 what? Length. So this is our formula. So now that you have this formula, right now you have this formula, you can now solve for A. So the next step is what? Trying to eliminate what? Free variable, which is what? Our free variable, which is what? A. If you look at our free variable in this equation, our free variable here, if you look at the free variable, is A. We are trying to eliminate what? A from this equation, right? So we are trying to eliminate A. So we make A subject to the formula. Making A subject to the formula, we now have what? A will now be equals to 6FL divided by rho F. Yes, 6FL divided by rho F. Not rho F, sorry, that's rho F. Yeah, rho F, or raised to power what? 2 divided by 3. That's our formula for A. So right now we now put this into what? The equation for material index. Because we know that our mass is equals to AL divided by AL times what? Density. And we're trying to what? Eliminate what? A. In order to eliminate A, we now do M is now equals to 6FL all over rho F, or raised to power 2 divided by 3 times length times what? Density. So next step is what? Step 4. Step 4, which is what? Break down the equation. So in order to break down this equation, we have to separate it into what? Functional constraint, geometric constraint, and what? Material property. In order to do that, we now look for mass is equals to, which of these is what? A material property. So the fracture strength is a material property, and density is what? A material property. So we now bring out material property, which is what? Density divided by fracture strength raised to power what? 2 divided by 3. That's our, then our length is what? The geometric constraint. So length is here. In order to bring them out, you have what? Length raised to power 5 divided by 3 as our geometric constraint. That's our geometric constraint. Then every other thing is what? A functional constraint, which is 6F raised to power 2 divided by 3. So this is what? Functional constraint. This is what? Geometric constraint. And this is what? Material property. Therefore your material index M is equals to density divided by rho F raised to power 2 divided by 3. And this is what? Minimize. Like I said, every time you have to leave your material property in terms of what? Maximization. So maximization, you have what? Density divided by. So in order to leave it in terms of maximization, you have to what? Find the inverse. So the inverse of this is rho f divided by 2 divided by 3 divided by density. So this is your material index. Okay guys, for this question, they have already defined or derived the function, constraint, objective and free variable for question 7.4. So you can take a second, pause the video and try and read the question, but they have already defined this for us. So we're trying to find the material index for a cylindrical column, for this particular column right here. So that's what we're trying to find, this material index for the column. So in order to do this, first we have to look at the function, which is the cylindrical column. The length is specified as a constraint, and the column must support a compressive load F without buckling. So this is what one of the constraint that we are looking for, right? And the objective is what? Minimize cost. So the other ones we've been looking at, we've been seeing what? Mass. So but this time we are looking at the cost of the column, right? So the free variable is what? The cross-sectional area A. So we are going to follow all the steps because we have A as the free variable and what? Choice of material, right? So we have to follow what? All the steps in this particular question. So step one, which is what? Derive objective function. That's step one. So the objective function in this particular scenario is what? Cost. If you look at the objective is what? Minimize cost. And we know that cost, if anytime you go to the market to buy a particular material, they tell you this is 1 kg. 1 kg of this material is equals to $5, or 1 kg of this material is equals to $10. So they always sell a material in terms of what? The kg. So it's always cost per kg times what? The mass. That's how they usually sell any material, cost per kg. So if you're trying to reduce cost, you're going to reduce what? The cost times the mass of the material. So cost C is equals to cost per kg times what? Mass. And I usually tell you that anytime you're defining what? The objective function, you have to define it in terms of what? The free variable A, because you're going to eliminate what? A at the end of the day, the free variable. So defining this in terms of what? A, it has to be cost is equals to C times C kg times what? Volume times what? Density. So if you want to derive it in terms of A, you have to break down volume in terms of A, which is what? Area, which is what? The cross-sectional area of this material, of this column, times the height. Times what? Density, then times what? C in kg. So this is what? The objective function that we're trying to define. So next one, we go to step 2. Step 2, which is what? Derive constraint function. So that's what we are trying to do in this particular step. So for step 2, we are trying to derive constraint function, so which is giving us this f critical, which is f is equals to what? N squared pi squared ei divided by h squared. That's the constraint function. Then I is also giving us, I is given in the question here as pi arrow 4, pi r raised to the power 4 divided by 4, or a squared divided by 4 pi. So our free variable is in terms of a, not arrow raised to the power 4. So we're gonna write our I is equals to what? A squared divided by 4 pi. So that's our a. So we have to put this I into this what? Equation of f. So f will now be equals to, so we now put I into it, will now be f is equals to what? N squared, which is pi, because this pi will now cancel this pi, e times what? A squared, or divided by 4h squared. So this is our equation for f. Right now we now make, since we are going to eliminate what? A at the end of the day, so we now make a subject to the formula. So a will now be equals to, we'll make a subject to the formula, we have what? Making a subject to the formula, we have 4f h squared all over what? N squared. If you remove n squared, then pi, then e, all raised to power what? 1 divided by 2, because of what? The square roots that you have here. So since you now have a, you now eliminate a from whatever we have in this objective function. You eliminate a from here. So all we have to do is what? Eliminate step 3. Eliminate free variable. So in order to eliminate free variable, let us write down our objective function again. F mass is equals to area times height times density times times C in kg, right? So we are eliminating A. So mass will now be equals to 4F h squared divided by n squared by E all raised to power 1 divided by 2 times h times density times cost per kg. So now we have this right now. We can now separate our, so step 4, break down equation. So in order to break down this equation, we have to separate this into what? Functional constraint, geometric constraint, and material property. So M, in order to write the material property first. So cost is usually a material property, cost per kg. So if you go to the market, aluminium has a different cost from steel and has a different cost from copper. So that's why you have cost is a material property. So cost is a material property, density is a material property, and Young's modulus is a material property. So you bring out all the material property as what? Density times what? Density times C divided by Young's modulus. So this Young's modulus has this what? Square root. So E raised to power what? 1 divided by 2. So next you now bring out what? Your geometric constraint. Your geometric constraint, the constraint is the height h. So the geometric constraint is height. So h here and h here, half will now cancel half. You now have half will now cancel the squared. You now have what? H squared times, then every other thing is what? A functional constraint. Every other thing in this equation is a functional constraint, which is f 4f divided by n squared pi all raised to power 1 divided by 2. So this is what? Functional constraint. This is what? Geometric constraint, and this is what? Material property. So M is equals to what? Density. Your material index is equals to kg divided by E raised to power 1 over 2. So this is what? Minimization, but you always try to leave it in terms of what? Maximization, right? So it's going to be E raised to power 1 divided by 2 divided by density times C in kg. So this is what? Maximization. So this is your answer.